Hello everyone. In this video clip today, I'm going to show you a very good technique to work with fractions. We're going to learn how to decompose the big fractions into a sum or difference of smaller fractions. Okay, and this technique is going to be pretty helpful when you guys get to calculus, especially calculus 2, and you got to do some integral, and partial fraction will help you to calculate the integral. Okay. But first, let me give you like the counter example, something that you guys learned a long time ago, I think, back into individual algebra. Say if you have two small fractions, how about 3 over x minus 2 plus 2 over x plus 1? And what if we asked you to add the two fractions together, combine the two fractions together? So then what did you do? You look for the LCD, right? The least common denominator, which is x minus 2 times x plus 1, right? So you're going to multiply the first fraction by the missing factor, which is x plus 1, times x plus 1 in here. Then similarly, times the second fraction by x minus 2, x minus 2. So the two fractions now have the same denominator. We call it common denominator. Now we're okay to add the two fractions together. And the answer will be 3x plus 1 plus 2 times x minus 2 over x minus 2 times x plus 1, and then you can simplify. 3x plus 3, I've distributed 3 into the two terms, plus 2x minus 4 over, bottom is what? X squared plus x minus 2x minus 2, 4. That's what I did. X times x is x squared. X times 1 is plus x, negative 2 times x, negative 2x, negative 2 times 1 is negative 2. Now I'm going to combine the right terms to have the answer. 3x plus 2x is 5x, plus 3 minus 4 is negative 1, over x squared minus x minus 2. So we started with 3 over x minus 2 plus 2 over x plus 1, and then we look for the common denominator. We multiply each fraction by the missing factor so that they have the same denominator, and then we put them all together, becomes one fraction. Simplify them by right terms, we have the answer. This is the sum of the two fractions. What we learn in this section today is the opposite procedure. We're going to start from here. What if we are given a fraction, and they ask you, what? Can you decompose that big fraction into the sum of two fractions right here? So you don't see the two small simpler fractions at the beginning. All you see is this. 5x minus 1 over x squared minus x minus 2. And the question asks you, what? How can you decompose this fraction to get back to this sum of the two small fractions? Okay? That was the idea. Alright, so it's pretty much we're working backward. So let me just mention something. You can only do it whenever the fraction is, let's call it, proper. Proper means what? You cannot have the numerator that is bigger than or equal to the denominator. This is called number. This fraction is proper. It's 3 over 7. The numerator is smaller than the denominator. But this one is not proper. Say 8 out of 3 or 7 out of 3. This is what? Improper. And how do you simplify this improper fraction, make it becomes proper? You do long division. Okay, this is what? 2, 8 divided by 3 is 2 plus 2/3. Okay, so you have the quotient and then plus a proper fraction. Okay, so always work with proper fraction. And in terms of polynomials, that's what we have right here. We are talking about degree. All right. In here, the numerator is of degree 1. The denominator is of degree 2. So yes, it is a proper fraction. Okay? If you have like degree 2 out of degree 2 is improper, or degree 3 out of degree 2 is improper. And you have to do long division to have the quotient and plus a proper fraction. And the partial decomposition right here, partial fraction decomposition we are learning today is applying to proper fraction. Okay. So let me skip the other step. We're going to start from the answer. Okay. How do we figure out the sum of two fractions from the proper fraction in here? like kind of backward step, right? So I'm gonna let me write up here so I have more room to write. 5x minus 1 over x squared minus x minus 2. I'm gonna start with the denominator. I have to factor this out to see all the factors out of it. So if I factor this out, I got x minus 2 times x plus 1. Okay, for the denominator. We learned how to factor already. Okay, now I see that I have two linear factors on the denominator. So I'm expecting to have two fractions when I decompose. And the first one is going to be something over x minus 2. The second one is going to be something over x plus 1. Since all the fractions are proper, the denominator is of degree 1, so the numerator is going to be degree 0. Same thing here, so it's going to be just a number. Let's call it a because I don't know what it is yet. B right here. And my job is to solve a and b. And hopefully a is going to be equal to 3 and b is going to be equal to 2. And we really have the answer. Okay, so the first step to decompose a proper fraction is to factor out denominators and list out all the possibilities for the denominators. In this case right here, I only have two factors, two linear factors to be more precise, x minus 2 and then x plus 1. So I expected to have two small fractions. Okay, so my job is to solve a and b. So if the fractions on the left-hand side equal to sum of two fractions on the right-hand side, so if I combine the two fractions on the right-hand side together, I should have a times x plus 1, and then here b times x minus 2, x minus 2. Now that all the fractions on the left and right hand side got the same denominator, and if they equal, then the numerator on the left hand side gonna be equal. Let me use a better word. The left hand side numerator is gonna be identical to the numerators on the right hand side. Another word, 5x minus 1 gonna be the same as a times x plus 1 plus b times x minus 2. Okay? You see, in the denominator on the left hand side, I got what? X minus 2 times x plus 1, right? And on the right hand side, I tried to make them the same denominator so that I force the numerator on the left the same as the numerator on the right. So I got to multiply the first fraction by the missing factor, which is x plus 1 now. A times x plus 1 over x minus 2 times x plus 1. And same thing is b right here, multiply by x minus 1, x minus 2, x minus 2. I got b times x minus 2 over the common denominator. Alright, now this equal to that. We have two ways to solve a and b from here. Let me start with the canonical way, okay? The formal method that we've seen over and over. Because this section is on the chapter of system of linear equations. So somehow they try to bring system of linear equation in here. Okay, so I'm going to factor the right hand side out. I got what? ax plus a plus bx minus 2b. Okay, it's equal to 5x minus 1. Right? Now let's combine the line terms in here. Group the term with x in it. I got a plus b times x and plus a minus 2b. And this is equal to 5x minus 1. So you guys see that on the left hand side you got a linear equation, right? 5 times x minus 1. So this 5 numbers go with the x term, and the negative 1 is just a number. And here what? A plus b goes to the x term, and then a minus 2b is a number. And if they're identical, means what? The left hand side is going to look exactly like the right hand side. So a 5x going to match up with a plus bx. And then negative 1 is going to match up with a minus 2b. And what does that mean? 5 going to be equal to a plus b. 5 going to be equal to a plus b. And negative 1 going to be the same as a minus 2b. And what do you see here? This is a system of two linear equations with two unknowns. And you can solve a and b from here. Say I do a subtraction. I got 6 is equal to 3b. See, 5 minus negative 1 is 6. A minus a is 0. B minus negative 2 is 3b. So I got b is equal to 2. After having b equal to 2 plug in, you can solve for a. 5 minus b equal to 3. So I got the answer is what? A is 3, so 3 over x minus 2, and then b is 2 over x plus 1. I got the fraction. Okay? That was the first method, and of course it works in here. You have system of two linear equations, two unknowns. What if you got more factors? What if you have like 3 or 4 or 5 factors? You should expect to have a system of 3 or 4 or 5 linear equations with 3, 4, 5 unknowns. Of course, it's gonna take more time to get to the answer. Okay, but that's the idea. Now let me show you another way to look at the problem, and we can explain this pretty much faster than this method. Okay, same idea, but we're gonna approach this from a little bit differently. Of course, we start the same way. We have a fraction, we factor out the denominator, we look for all the possibilities for the partial fraction, and we end up with the numerator on the left-hand side, and then to go to the numerator on the right-hand side. Here, instead of doing distribution, multiply a to other term, b to other terms, we argue this way. Since this equation, this expression works for any x, right? It's true for any x. Why don't we just try some special x? I'm going to choose x equal to 2 to plug in here. You see why? Because if I plug in x equal to 2, this is a 0 for this factor, so we can cancel out the b, and it still works. And hopefully I can solve for a from here. Say, plug in x equal to 2. What you got? 5 times 2 minus 1, 2 for x. Okay, so 10 minus 1 is 9, equal to x equal to 2. 2 plus 1 is 3. 3 times a is 3a. 2 minus 2 is 0 times whatever b is. 0, and I can solve for a directly from here. A is equal to 3. Isn't it a little bit faster? Same thing. If I plug in x equal to 2, I can solve for a. What if I plug in x equal to negative 1? Okay. 5 times negative 1 is negative 5, minus 1 is negative 6, equal to negative 1 plus 1 is 0 times a 0. Well, what about the b term? Negative 1 minus 2 is negative 3, and b is negative 3b. And obviously b is 2. See? Only 2 lines. With this particular example, we have the answer right away without going through the system linear equation. 2 linear equations with 2 unknowns. Okay. So hopefully via the first example, you guys have some ideas of partial fraction decomposition. We learned basically how to decompose, how to break a big fraction out into the sums of smaller fractions. And I claim that this technique is going to be very useful for you guys, very helpful when you guys get to calculus. I think it's Calc 2, when you have to deal with integration. You don't know how to integrate a big fraction, break it out with it. And then you can integrate a smaller fraction. Right? But that's for the later story. For now, we learn how to decompose a fraction. Let me give you the general rules, and then after that, I'll give you more examples. Okay. How about another example? But this time, I'm not going to solve the whole thing. Okay, I'll just show you how to decompose a big fraction out. Say you got 3x plus 1 over, how about x plus 2 cubed times x minus 1 squared times x squared plus 1 squared. Cube that, make it bigger. Doesn't matter. So in here, I will show you this is a huge fraction with linear factors and quadratic factor in the denominator. This with multiplicity. So x plus 2 with multiplicity 3, x minus 1 multiplicity 2, and then this one is what? X squared plus 1 with multiplicity 3. And by the way, as we learned before, I claim that if you have a polynomial of rational coefficient or integer coefficient, you can always be able to factor out as the factors of the product of factors, what, linear or quadratic, okay? And if you have a cubic, it means that you can always be able to factor it out into a linear times a quadratic. You have a polynomial degree 4, you can always factor as what? 4 linear factors, or product of 2 quadratic factors, or 2 linear and 1 quadratic, okay? So anyway, it's always come down to linear or quadratic. Now, get to this one. And first question is it proper? Yes. numerators of degree 1 only. Look at the denominator. Degree 3, degree 2, degree 6. So degree 2, 6 is like degree 11. So it's very proper. Okay, so how do you decompose it? We're going to take care of one factor at a time. Okay, let's start with the first factor. I have x plus 2 is a linear factor, but I got multiplicity 3. So I'm expecting to have 3 fractions, 3 partial fraction with x plus 2. The first one going to be x plus 2. The second one going to be x plus 2 squared. And the third one going to be x plus 2 cubed. Okay? And just listen at all the possibilities for the partial fraction that's involved in the factor of x plus 2. So I have 3 possible fractions. Could be just x plus 2, could be x plus 2 squared because I got cube totals, and then x plus 2 cubed. So linear up to multiplicity, the numerator is going to be just degree 0, so numbers, so A, B, and C. And similarly, the second factor is x minus 1 with multiplicity 2. So I am looking at 2 possibilities for the second factors. I got x minus 1 or x minus 1 squared. And of course, linear up to multiplicity, I have just a number on the numerator, so it's going to be A, B, C, and then D, and then E. Now, let's move on. The third factor is not linear anymore. But we just talked about multiplicity now. We got linear multiplicity 3, right? So I'm going to have 3 possible partial fractions. Could be x squared plus 1, could be x squared plus 1 squared, or could be x squared plus 1 cubed. Now, here comes the difference. On the numerator, since the denominator is of degree 2, the numerator could be degree 1. So it's going to be what? E and then fx, A, B, C, D, E, F, G, H, I, J, K. All right? This is how you decompose a big fraction out into the sum of a bunch of partial fractions. And you have to solve a system of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 equation with 11 unknowns. Okay? A all the way to K. That was the idea. Of course, we're not going to do it in our clip. We are always try to give you an example of system of 3 or 4, I think, around there. 4 unknowns, and then we can solve it. All right, but this is just the idea. Okay? Now you get the main idea. Let me show you a couple more examples. I'm thinking of maybe 2 more, and we call it the day. Okay, let me look for another one. Example. This is not good. Just choose a problem in the book. Okay, I see one. 8x minus 14, 8x minus 14 over x minus 1 times x plus 2 times x minus 3. X minus 1, x plus 2, x minus 3. So in here, the numerator is a polynomial of degree 1, denominator is polynomial of degree 3, and it's very nice that the book already factored out the denominator for you. So you have 3 linear factors, okay, with all multiplicity 1. All right, so we're going to take care of one factor at a time. X minus 1 with multiplicity 1. I am having 1 partial fraction. And linear, so it's just a number on top. Okay, same thing, x plus 2 with multiplicity 1. X plus 2, just be up here, and then x minus 3, C. No multiplicity, on multiplicity 1 I mean. Alright, so you have to solve for 3 numbers, A, B, and C. Alright, and to have the left hand side equal to the right hand side, the idea is that we try to make the same denominator, so the common denominator is right here on the left. So that means on the right hand side, first fraction we have to multiply back by x plus 2 and x minus 3. X plus 2, x minus 3. The second fraction we have to multiply back by x minus 1 and x minus 3 because we got x plus 2 already. Okay, x minus 1, x minus 3. The third fraction we have to multiply back by x minus 1 and x plus 2. X minus 1 and x plus 2. And you see the purpose of this is to make all denominators the same, so you can work in the numerator. And if the fraction on the left hand side equal to the sum of the fractions on the right hand side, the numerator on the left, which is 8x minus 14, that will be equal to the numerators on the right, which is a times x plus 2 times x minus 3 plus b times x minus 1, x minus 3 plus c times x minus 1, x plus 2. All right? And with the very first method that I show you, you're going to multiply them all out, combine the right terms, and I think that's going to be a lot of work. So let me go straight to the second method that I just showed you. I'll plug in some value first, and I'll solve for a, b, and c. Try x equal to, how about 3? You see why I chose 3? Right here, right? 3, and what? 8 times 3 is 8 times 24 minus 14 is 10. 3, the first term is going to be 0 because 3 minus 3 is 0 times whatever is 0. Same thing, second term is 0. What about the third term? 3 minus 1 is 2. 3 plus 2 is 5. So 2 times 5 is 10, so it's equal to 10c. So c is 1. How quick is it? Try another one. X equals to negative 2. Negative 2 times 8 is negative 16 minus 14 is negative 30. Of course, negative 2 make the first term 0. And of course, the last term is 0 as well. Negative 2 plus 2 is 0, right? What about the b term? Negative 2 minus 1 is negative 3. Negative 2 minus 3 is negative 5. Negative 3 times negative 5 is 15. So it's equal to 15b. So b is negative 2. Okay? Now, x equal to 1, right? X equal to 1. 8 times 1 is 8 minus 16 is negative 6, right? Yeah. 8 minus 14, minus 14, I mean, it's negative 6. And 1 in here, 1 plus 2 is 3, 1 minus 3 is negative 2. So 3 times negative 2 is negative 6, so it's negative 6a. What about the b term? 0, c term 0, so a is 1. And then you have to answer the question, right? 8x minus 14 over x minus 1, x plus 2, x minus 3, got to be equal to 1 over x minus 1 plus negative 2 over x plus 2 and plus 1 over x minus 3. That's going to be your answer. You decompose the big fraction right here into the sum of 3 smaller fractions. All right. Let's write one more example. Let me look for something that's got quadratic in it. Okay, number 49 is a good one. See what we have in here, 49. We have x minus 1 over x plus 1 squared, everything squared, times x squared plus 2x plus 2. Okay, first you have to check, see if the fraction is proper. Top is degree 1, the bottom is degree 2 plus degree 4. Okay, so yes, it's proper, so you can decompose it. They factor out for you right here. This is linear factor with multiplicity 2. This is quadratic. Be careful. You have to check to see if this quadratic is factorable. And I claim in this case it's not factorable. You can use quadratic formulas to solve and see if you don't have real solutions. So this is irreducible. That's how they call it. It's not factorable. So everything is factored out nicely for you. So all you have to do is look for the decomposition of partial fractions. Okay. So we start with the first factor, x plus 1. We multiply 2. So I'm expecting to have 2 partial fractions coming out of the first factor right here. It could be something over x plus 1 and then something over x plus 1 squared. Now it's linear up to multiplicity. The numerator is going to be just a number, so called a here and b there. And the next factor is x squared plus 2x plus 2 with multiplicity 1. So I'm expecting to have just one fraction. Okay, and this is linear. We have linear. I'm sorry, it's quadratic. Let's take it back. It's not linear, it's quadratic. Degree 2. So to have a proper fraction out of it, the numerator could be a polynomial of degree 1. So it's going to be cx plus d. And keep in mind that c could be 0 or d could be 0, who knows, okay? So I have a sum of 3 fractions. If I want to decompose this big fraction on the left-hand side, my job now to solve a, b, c, and d. Okay, and again, repeat the same step. I'm going to multiply back to have the LCD right here. So the numerator on the left will be x minus 1. The numerator on the right-hand side for the first term, what do I need to multiply back? I need to multiply back x plus 1 and x squared plus 2x plus 2. Okay. A times x plus 1, x squared plus 2x plus 2. Because I need to have x plus 1 squared, I got one term right here ready. Multiply back with x plus 1 and then x squared plus 2x plus 2. Right, so get the common denominator. For the b term, I'm going to multiply back by x squared plus 2x plus 2 because I got x plus 1 squared ready. And for the c term, c and d term right here, cx plus d. By the way, you have to write the whole numerator in parentheses, okay? And then multiply back by x plus 1 squared. So this is the equation for numerator on the left, and then it goes to numerator on the right. And first method say what? You have to multiply them all out, combine the line term to solve a system linear equation. Doable, but in my opinion, too much work. So we're going to plug in some numbers. I think it'd be easier. Try, say, x equal to -1. See why I choose -1? This is a factor, right? -1. Hopefully I can solve something. Try x equal -1. I got left hand side is going to be -2. -1 minus 1 is -2. The a terms cancel out because of what? -1 plus 1 is 0 times whatever is 0. The last term also cancel out. -1 plus 1 is 0 times the whole thing is 0. What about the b term? -1 squared is 1. 1 plus 2 is 3. -1 times 2 is 2. So 3 minus 2 is 1. So it's just b. I got the answer right away. So far, so good. Okay. So at least I plug in one value. I got the answer for b. Now try another value. So plug in for x. Sometime or many times I would say you cannot avoid the system linear equation, but what if you can solve for something and your system is going to be smaller, which is easier to solve. So I strongly encourage you guys to do that. And by the way, when you guys get to calculus, the whole thing that we are learning today will be just a small portion for solving a bigger problem later, which means you don't have a lot of time to go over this again. It means what? You have to take care of this partial fraction real quick and correctly. So I strongly encourage you guys to use this way. Okay, now I'm going to try another value. I see that there's no solution, no real solution, so let's try x equals 0. See why? And I plug in x equals 0, I can cancel out the c term. Okay, try x equal to 0. See what we got? -1 is on the left. The right hand side is what? 0 plus 1 is a, right? 0 plus 1 is 0. 0 plus 1 is 1, I mean. 0, 0, 2, right? So 1 times 2 is 2. So this is 2a. Okay. X is 0, what?